Hi, this is Srivatsan. I'm a graduate student at the ACES lab in University of Florida, and today I'm going to be presenting our work on Bandit-based runtime adaptation of cache replacement policies in content management systems. Recent years has seen an exponential growth of the internet, which has led to an increase in the complexity of the data being accessed by users. The complexity arises due to the geographical distribution of requests, the type of data that's being accessed, the size, and the inherent variability associated with the access pattern. Typically, content providers introduce a cache between the client and the web server in order to improve the response time as perceived by the user and also to decrease the network bandwidth and web server usage. In practice, cache sizes are significantly smaller compared to the total content served by a web server. Thus, a cache tends to become full pretty quickly. When a request arrives at the cache, the cache is first checked to see if a response for that particular request is available. If it's so, then the response is returned to the client and it's marked as a hit. If the response is not found, then the request is forwarded to the server and the response from the server is first stored in the cache before it's returned to the client. There are two classes of algorithms that help in deciding the action to be taken when a new object arrives and the cache is full. Replacement policy is a type of algorithm which helps in deciding which object or data that's in the cache to be replaced for the new object. Commonly known replacement policies are LRU and LFU. Admission policy is a different class of algorithms which help in deciding whether the new object must be inserted into the cache or not. A cache is only as effective as its replacement policy, which determines the hit ratio of the cache or the performance. In turn, the performance of the replacement policy depends on the pattern of the data requests themselves. We know that the data access pattern changes over time due to the changing interests of the user. Thus, a fixed replacement policy cannot provide optimal performance, motivating research on dynamically adapting the replacement policy based on the data access pattern. Before we proceed, I would like to introduce multi-arm bandit. Multi-arm bandit problem is a problem where there are multiple options available to choose from, with each choice yielding varying rewards. The goal being to determine the best or the most profitable outcome through a series of choices. Initially, the odds of winning and the payouts are unknown, that is, the reward distribution for each choice or option is unknown, and the reward distribution varies across the available options. Simply put, MAB problem is how to efficiently identify the best choice available while sufficiently exploring the many options. MAB tries to achieve this through two different processes. It selects different choices at random, which is called as exploration, and it tries to choose the best choice or the choice that yields the highest payout, which is classified as exploitation. The reward obtained from making a choice is recorded or maintained, and history of rewards for all the choices are maintained in order to facilitate exploitation. Efficient balancing of these two phases is required because too much exploration will lead to suboptimal reward and too much exploitation could lead to a scenario where a better performing choice has not been explored. Algorithms have been developed to find the sweet spot. We'll be discussing two such algorithms in this talk. The first one is epsilon greedy algorithm, which is a type of greedy algorithm with epsilon being a tunable parameter that determines the probability with which MAB will choose the exploration phase. The performance of the epsilon greedy algorithm depends on the choice of the epsilon parameter, and for a poorly chosen epsilon value, the epsilon greedy algorithm will converge in a suboptimal solution. The next algorithm would be Thompson sampling, where there are no tunable parameters, and it uses a posterior distribution to identify the probability of the rewards. It has an inherent mechanism to switch between exploration and exploitation phases, and it has been shown to converge to global optimal solution. We introduce a new metric called rank, which will be used as the reward for MAB. Rank is defined as the index or position of the object with reference to the LRU object or LFU object. Let's see this through an example. Let's assume there are 5 objects in a cache A, B, C, D, E, and this is the representation in the LRU metadata, with A being the LRU object at the head of the list and E being the most recently used object at the tail of the list. Now computing the rank of D, we see that the index of D is 3. Thus the rank in the LRU metadata is 3 for D. For convenience, we compute the normalized rank. for over the total number of objects at the cache at any given time. Thus, the normalized rank with respect to the LRU metadata of D is 0.6. Let's take a look at how the LFU metadata looks like. Note that the ordering of the object is different because in LFU metadata the ordering is based on the reference count. Thus, B becomes the LFU object with reference count of 1 at the head of the list, and A becomes the most frequently used object in this particular list at the tail. Computing the rank of D, we see that the index of D in LFU metadata is 1, thus the rank of D with respect to LFU metadata is 1, and the normalized rank becomes 0.2. Works in adaptive cache could be broadly classified into two, one being replacement policy, the other being cache size. In cache size, the size of the cache is adjusted dynamically at runtime to improve the performance of the cache, whereas in a replacement policy technique, the cache is adapted to favor either the recently used objects or the frequently used objects with the goal of improving the performance. In this talk, we'll be focusing on replacement policies. The first one being ARC or adaptive replacement cache, in which the cache is divided into two LRU lists. The size of the lists are dynamically adjusted to adapt to the changes. List 1 stores the objects that are seen only once, which indirectly refers to the LRU cache. And list 2 stores the objects that are seen at least twice, representing indirectly the LFU cache. ARC maintains ghost entries equal to the size of the cache, and it has been shown to not adapt quickly to changes in the access pattern, and it doesn't work well for smaller cache sizes. The next work we'll be discussing is LECAR, which is a reinforcement learning based approach that focuses on LRU and LFU replacement policies. It uses regret minimization technique to identify the probability distribution of the replacement policies. It maintains two lists of ghost entries, one for LRU and one for LFU, with the size of each list being the same size as that of the cache. They maintain weights for each of the replacement policy, which are then dynamically adjusted at runtime. The history of objects are maintained to compute the regret, and the regret for a miss on an object evicted recently is computed to be larger than the one that is evicted in the past. LECAR maintains ghost entries. The third work that I'll be discussing is an admission-based policy, which is called Tiny LFU. It uses counting Bloom filter to maintain an approximate representation of the frequency count of objects. They maintain LRU cache where the actual objects are stored, and the evicted object, that is the LRU object, is then compared to the new object using the information from the Bloom filter in order to decide whether the new object should be placed in the cache or not. Access frequency of older objects are maintained in the Tiny LFU technique. We propose DETACH, an adaptive mechanism that reuses existing replacement policies such as LRU and LFU to adapt to the changes in the access pattern, and we achieve this without maintaining any history or ghost entries. Let's take a look at how DETACH works. We see a typical cache system which provides us with the information of a hit or a miss for every request that it receives. DETACH then monitors the hit or miss information, and upon a miss, computes the rank using the metadata available. The rank of the evicted object is then fed into the controller, which then makes an adaptive decision. Multi-armed Bandit is integrated as the controller to make the adaptive decisions at runtime, and Thompson sampling algorithm is used to switch between the exploration and exploitation phases of the multi-armed Bandit. We focus on two replacement policies in this work, LRU and LFU. However, note that other replacement policies could be integrated with this work as well. Let's see how the rank of the evicted object is used by MAB towards decision making. At time t0, MAB starts with LRU as the active replacement policy. Note that the replacement policy plays its role only when the cache is full. The rank from the inactive replacement policy, that is LFU, in this particular case, is considered by MAB towards decision making. We'll see why. Let's assume that the cache becomes full at time t prime and a new object arrives. Since this is the first object after the cache is full, the LRU element is chosen, which is A in this particular case. Computing the rank of A with respect to the LRU metadata, we see that it is 0, and the rank of A with respect to the LFU metadata is 1 since it's the most frequently used object. We can clearly see from this example that the rank of the evicted object with respect to the active replacement policy is always 0, and we only obtain useful information from the rank of the same object with respect to the inactive replacement policy. Thus, when we refer to rank of evicted object, we always refer to the rank computed from the inactive replacement policy. Moving on to the feedback controller, DETACH uses Thompson sampling as stated earlier. A cache system is actually a Bernoulli bandit problem since the outcome is usually a 0 or 1 representing miss or a hit. However, in our case, it becomes a continuous Bernoulli bandit problem since we consider the outcome to be the normalized rank of the evicted object which lies in the interval 0 to 1. DETACH uses the beta distribution as the posterior distribution in order to exploit the conjugacy property between the Bernoulli distribution and the beta distribution. Beta distribution has two parameters A and B, which are also called as a shape parameters, which help in determining the mean and standard deviation of a Gaussian distribution. Let's look at some examples of A and B values. When A is 1 and B is 1, we see that the beta distribution represents a uniform distribution, and for values A, where A is larger than B, we see that the mean shifts towards the higher values of X. And for A being smaller than B, we see that the mean shifts towards the lower values of X. Now the shape parameters A and B are tracked for both the policies, and as and when the rank information is available, that is, whenever an object is evicted and the rank is computed, this information is then used to update the shape parameters. Once the shape parameters are updated, random samples are drawn from these updated distributions, and the maximum of the random samples is then chosen as the policy, as shown in algorithm 2. While working on DETACH, we came across a special scenario where the LRU object is the LFU object as well. Thus, the rank of the evicted object becomes 0, and this impacts the controller negatively because the shape parameters are not updated. Since the shape parameters are not updated, Thompson sampling switches to the exploration mode and thus results in a suboptimal solution. Empirically, we found that scan jobs create such scenarios. And it's also very well known that LFU replacement policy is a scan resistant policy. Thus, when the controller, or MAB, detects the rank of the evicted object as 0 at runtime, we drive the system to favor the LFU replacement policy. This helped in improving the performance of the cache for such traces. Towards this, we actually implemented a simple cache to test DETACH. Our cache is different from the regular cache in which we maintain both LRU metadata and LFU metadata for each object. This is the only storage overhead in implementing this particular cache. The LRU metadata is then used to compute the LRU rank, and LFU metadata is used to compute the LFU rank. In our cache implementation, the LRU metadata is implemented as a doubly linked list. Thus, to compute the rank, the list is traversed, and which results in an order of n operation. The LFU metadata is implemented as two doubly linked lists, with one doubly linked list containing the frequency count and the other doubly linked list containing the metadata under the respective frequency counts. The rank computation in both the lists thus becomes an order of n operation. To improve the performance, we approximated rank using the following formulae. In LRU metadata, the rank is computed with respect to the access time or the last access time of the object, and it's normalized to the last access time of the LRU object. With respect to the LFU metadata, the rank is computed simply using the reference count of the object. Thus, after the approximation, the rank computation becomes an order of 1 operation. We conducted various experiments to compare the results obtained after rank approximation and before rank approximation, and we found that there were no difference in the results. All experiments were conducted on cache sizes between 0.5% and 5% the total size of the dataset. This was done because we observed a significant difference in the performance between LRU and LFU replacement policies for the said window. Average hit ratio at the end of each run was computed, with hit ratio being the number of hits over the total number of requests as seen by the cache. We report results comparing DETACH to LECAR and the baseline LRU and LFU replacement policies. In order to test the adaptive nature of DETACH, we used a synthetic workload. The synthetic workload consists of alternating LRU and LFU favoring requests in 4 phases shown by the green partition. This plot shows that the DETACH and LECAR are able to adapt quickly to the changing conditions. After a brief dip at the end of the second phase, we can see that DETACH is ramping up faster compared to LECAR. The plot proves that DETACH is able to adapt to the varying conditions in the workload. Next, we show the performance of DETACH in the search engine workload. This is a special case where the rank of the evicted object is 0. We can see that DETACH outperforms LECAR by a factor of 2 for cache sizes of 0.5%, 1% and 2%. LECAR and DETACH perform the same when it becomes 5%. Next, we present the results obtained from testing DETACH with P1 workload. P1 workload consists of traces obtained from Windows servers. Here, LECAR outperforms DETACH for cache sizes of 0.5%, 1% and 2%. At 5%, DETACH and LECAR perform the same. This is due to the nature of the P1 workload, where few objects are requested large number of times with an inter-arrival rate that is larger than the cache size, but small enough to be preserved in the history list maintained by LECAR. LECAR is at an advantage here because they maintain the metadata of the evicted object in the history list, such as the frequency count. When a request for an object present in the history list arrives, the object is stored in the cache with the last state from the history list, such as the frequency count. DETACH is at a disadvantage here because when an object arrives, when a request for an object that has been evicted from the cache arrives, it is always treated as a new object and it's placed at the less frequent side of the cache where the object is subjected to immediate replacement. To conclude, DETACH utilizes existing replacement policies such as LRU and LFU. It was designed with the ability to integrate easily with existing cache implementations. It does not use any history or ghost entries to adapt the cache at runtime. DETACH uses Thompson sampling and exploits the Beta-Bernoulli conjugacy property by utilizing beta distribution as the posterior. It uses rank of the evicted object, which indirectly characterizes the runtime request patterns to make decisions about the replacement policy. Through this work, we also identified a unique property with LFU favorable data traces. We implemented a simple cache system to demonstrate the working of DETACH. We tested DETACH with 7 different data traces that are available from previous work. In LFU favorable data traces, DETACH outperformed LECAR by a factor of 2 without maintaining any history. In this work, we focused primarily on the 2 commonly known replacement policies, LRU and LFU. However, other replacement policies can be integrated. When comparing with other works, it is observed that there is room for improvement. Thereby, other forms of reinforcement learning must be explored to bridge the gap. Thank you for your attention.